Hello everyone. There are many reasons why a small power supply solution size is beneficial. Maybe you're trying to shrink the overall size of your system or adding more functionality elsewhere on the board without growing the PCB dimensions. Well, today we are going to talk about how DC-DC power modules can shrink power supply size and save board space without sacrificing thermal performance. First, let's take a look at a 3 amp discrete buck converter solution and compare it to a parametrically equivalent integrated inductor module solution. The total BOM size of the buck converter solution, including the discrete inductor, input and output caps, and resistors to set the 4-volt output voltage, takes up an area of 36 square millimeters. This translates into a power density of 333 watts per cubic centimeter. For comparison, on the right side, we have the same regulator but built into an integrated inductor module. The module occupies only 23 square millimeters and increases the power density to 470 watts per cubic centimeter. So, I think we can all agree that the higher integration offered by power modules can lead to substantial space savings. But does that mean we have to sacrifice thermal performance? The short answer is no. But how is this possible? The biggest reason is that packaging technologies have advanced over time. Using the same devices from our previous comparison, the module solution has a lower junction to ambient thermal resistance, which is a measure of how easy it is to move the heat inside the module to the ambient environment. Also, there are no bond wires, and internal routing is optimized inside many of our latest modules, further reducing losses that come from parasitic resistance and inductance. Modules utilize special lead frames that enable this routing optimization and, more importantly, transport the heat from the module into the PCB. The right integrated inductor, along with a module package with good thermal design, is what enables modules to provide great efficiency and robust operation. Now, let's take the theory and put it into practice. We'll do that by taking a closer look at the thermal behavior of a module on a PCB, which in this case will be a device evaluation board. Using the TPSM 82866 6-amp buck module as an example, I'm going to walk you through the process of using a device EVM as a blueprint to achieve impressive solution size and great thermal performance. Before the first boards are built, simulations are conducted based on JEDEC standards. A second simulation is then completed based on the real-life parameters of the evaluation board, which is also something that we make available in the EVM User's Guide. Once these simulation results look good, the boards are built and the real hardware undergoes further testing. Utilizing IR cameras and a thermostream allows us to test the board under many different conditions. Fully understanding all thermal characteristics of a device is an essential part of completing a robust power supply design. This is where the Safe Operating Area Curve, or SOA, comes into play. The results of all that extensive testing on the EVM is reflected in these SOA curves, which allow engineers to easily understand the module's operating conditions and simplify the process of design optimization. So, we started with the theory of how power modules provide great size and thermal performance. But then we provided the design blueprints with the EVM and fully characterized its performance via the SOA curve in the datasheet. Because of all these painstaking efforts put forth by our power module designers, we are able to offer you a higher density and more reliable product. If you learned one thing in this training, let it be this: power modules can deliver the high density you are looking for and with great thermal performance, all with less design effort compared to discrete solutions. Visit ti.com/powermodules to find your next power module. Thanks for watching.